To solve this equation, we begin by looking at the knowns. So the mass of the astronaut is 80 kilograms, the mass of the satellite is 640 kilograms, and the force exerted on the satellite by the astronaut is 100 newtons. Because of Newton's third law, we know that there is an equal and opposite reaction on the astronaut by the satellite, and the equal part lets us know that it is equal to 100 newtons. Using these numbers, we can find the value of the acceleration using F equals mass times acceleration. So for the astronaut, that will be 100 is equal to 80 acceleration. And for the satellite, that will be 100 is equal to 640 acceleration. The results for these equations are 1.25 meters per second squared and 0.156 meters per second squared. Now that we have acceleration, along with a time and an assumed initial velocity, we can use kinematic equations to solve the rest of the problem. So the first kinematic equation we'll use is to find the final velocity at the end of the period of acceleration. And that will be velocity final is equal to velocity initial plus acceleration times time. We are assuming that the initial velocity is 0, so we do not have to worry about that. So the final velocity for the astronaut is going to follow this. That final velocity is equal to 0.625 meters per second. Then we do the same thing for the satellite. So the same equation, ignoring initial velocity. We get an answer of 0.078 meters per second. Now that we have our final velocities at the end of the period of acceleration, we can use those to plug everything back in to find the displacement during that time. And that equation will be displacement is equal to 1/2 of initial velocity plus final velocity and the time. For the astronaut, we are once again assuming initial velocity is 0, so that will just be the final velocity. Then there's 0.5 seconds of acceleration. And the result for that is 0.156 meters during the period of acceleration. We do the same thing for the satellite. And our result is 0.0195 meters. Now, this is the distance traveled during the period of acceleration, but there's also 60 other seconds that it is moving apart. This part is a bit easier because we know our final velocity at the end of acceleration, and it's going to stay constant because we are in space, so we are not taking into account friction and gravity and some forces like that. So we can just take the final velocity and multiply that by 60 seconds. When we do that, we get 37.5 meters. Then we would do the same thing for the satellite. And we get 4.68 meters. So these four displacements are going to come together to form the distance between the astronaut and the satellite. And when we add all of those up, we have 42.36 meters between the astronaut and the satellite. In the original equation, we have 1 sig fig, so we'd round that up to 40 meters if you're following sig figs. And we do not take into account negatives and positives between the distance because it's just asking how far apart they are. So you would add all of those with no negative signs included.